Sorry for the interruption in the previous topic. Now we will see the next topic, colligative properties. Now, colligative property is a property which depends only on the number of particles present relative to the total number of particles present in the solution. That is, number of solute particles relative to the total number of particles present in the solution and not on the chemical nature of the solute particles. The important colligative properties are relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. We will see each one separately. First, relative lowering of vapor pressure. And the meaning of lowering of vapor pressure is already known to you. When a non-volatile solute is dissolved in a volatile solvent, vapor pressure decreases. And this is called lowering of vapor pressure. And that is, if P10 is the vapor pressure of the pure solvent and P1 is its vapor pressure in the partial vapor pressure in the solution, P10 minus P1 is called lowering of vapor pressure, and that is equal to delta P. So delta P is the lowering of vapor pressure, which is P10 minus P1. And now, but we know, since the solution obeys Rolle's law, P1, this P1 is equal to P10 into mole fraction of the solvent. Substituting this here, we can write, and that is, we can rearrange and write delta P is equal to P10 minus P1, but P1 is P10 into X1, mole fraction. Taking P10 as common factor, we can write this as, this is equal to P10 into 1 minus X1. But 1 minus X1 is X2, and that is, this is equal to P10 into X2, where X2 is the mole fraction of the non-volatile solute. This we get because we know X1 plus X2 is equal to 1, and therefore delta P, that is lowering of vapor pressure, is equal to P10 into X2. And now if we rearrange this, we can write it as delta P divided by P10 is equal to X2, and that means delta P is P10 minus P1, and hence this equation can be written as P10 minus P1 divided by P10, and that is equal to X2. And this is called relative lowering of vapor pressure. So the ratio between lowering of vapor pressure and vapor pressure of the pure solvent is called relative lowering of vapor pressure, and that is equal to mole fraction of the non-volatile solute. And if we know the number of moles of the solute and the solvent, we can find the mole fraction of the solute. So if N1 and N2 are the number of moles of solvent and solute respectively, this is equal to N2 by N1 plus N2, where N1 plus N2 is the total number of moles. Then in a dilute solution, we will find N2, number of moles of solute, will be very less compared to the number of moles of solvent. Therefore, N1 plus N2 will almost be equal to N1, and therefore we can write this equation as P10 minus P1 by P10 is equal to, almost equal to N2 by N1. Then, if W2 is the mass of the solute and M2 is the molar mass of the solute, also if W1 is the mass of the solvent and M1 the molar mass of the solvent, we can substitute for number of moles. Substituting, we will get this is equal to, number of moles is equal to mass by molar mass, and therefore this is equal to W2 by M2 by N1, but N1 is equal to W1 by M1, and therefore we will get this into M1 by W1. Now the significance of this is that using this, and this means this is relative lowering of vapor pressure. Using this colligative property, we can find the molar mass of a non-volatile solute. So for this we have to take a known mass of the given solute, dissolve that in known mass of the solvent, prepare the solution, find out the lowering of vapor pressure. And knowing this, we can find molar mass of non-volatile solute. So this is an experimental method to find molar mass of non-volatile solute using the colligative property, relative lowering of vapor pressure. The next colligative property is elevation of boiling point. Now elevation of boiling point is also because of the lowering of vapor pressure. When a solute is dissolved, we know the vapor pressure decreases, and therefore boiling point of the solution will not be same as the boiling point of pure solvent. As you know, boiling point is the temperature at which vapor pressure becomes equal to external pressure. When in a pure solvent, when we dissolve a solute, vapor pressure decreases. So it's very clear the solution will not will not boil at the temperature at which pure solvent boils. We will have to heat the solution further so that its vapor pressure becomes equal to external pressure. And that means a solution boils at a temperature which is higher than the boiling point of the pure solvent. This increase in the boiling point is called elevation of boiling point, represented by delta TB. Elevation of boiling point. And so boiling point of the solution is higher than that of pure solvent. So pure solvent, if boiling point of pure solvent is TB0 and boiling point of the solution is TB, then delta TB is equal to TB minus TB0. Boiling point of solution is more than that of pure solvent. This difference in boiling point is called elevation of boiling point. And it has been experimentally shown that this elevation of boiling point delta TB is directly proportional to molality of a solution. So we can write this relationship: delta TB is directly proportional to molality, small m, of the solution. And this means delta TB is equal to a constant. That constant is represented as Kb into m, that is molality. And if we consider this constant Kb is called elevation, boiling point elevation constant, or molar elevation constant. Also, it's also known as ebullioscopic constant. Ebullioscopic constant. So boiling point elevation constant, molar elevation constant, or ebullioscopic constant. And we can define this ebullioscopic constant from, or boiling point elevation constant from this equation. If m equals 1, we find delta TB will be equal to Kb, and that means boiling point elevation constant is the elevation of boiling point when molality is 1. Molality 1 means for a solution having 1 mole solute dissolved in 1 kilogram of solvent. And from this, normally delta TB can be expressed, of course, in degrees Celsius or in Kelvin. And molality, unit of molality, number of moles present in 1 kilogram, moles per kg. And therefore, unit of Kb will be Kelvin, kilogram per mole. Kelvin, kilogram per mole will be the unit of ebullioscopic constant or boiling point elevation constant. And this boiling point elevation, delta TB, can also be represented graphically. Now here, vapor pressure is plotted along the y-axis, and here temperature. So variation of vapor pressure with temperature of solvent and solution can be represented. Now as temperature increases, vapor pressure increases. So vapor pressure of solvent varies along this line, this curve. Its solution has a lower vapor pressure. So at a given temperature, vapor pressure of solution will always be less than that of pure solvent. And therefore we get the curve of the solution below that of solvent. And this point stands for 1 atmospheric pressure. And boiling point, normal boiling point, is the temperature at which vapor pressure becomes equal to 1 atmosphere. And therefore here this vapor pressure then becomes 1 atmosphere, we can find the corresponding temperature from the temperature axis, and that means at this temperature solvent boils, and therefore this will be the boiling point of pure solvent. And same way for solution, the boiling vapor pressure becomes equal to 1 atmosphere at a higher temperature, which we represent as TB. And this difference between the boiling point of the solution and the pure solvent is called elevation of boiling point, delta TB. And so using delta TB again, like relative lowering of vapor pressure, we can find the molar mass of a non-volatile solute, and that is the delta TB is equal to Kb into M. M is molality. Substituting for molality, this is equal to Kb into molality is number of moles of solute, or solute is 2, represented by 2. So number of moles of solute divided by mass of the solvent, W1, given in grams, into 1000. But number of moles is equal to number of moles N2 of the solute is equal to mass of solute divided by molar mass of solute. Substituting this in here in the equation, this now becomes, equation becomes delta TB is equal to Kb into, instead of N2 we can write W2 by M2, and therefore this is W2 by M2 divided by W1, and here into 1000. And again, significance of this equation is that using this we can find the molar mass of non-volatile solute, and that is a non-mass. From this we can derive the equation for M2. So M2 is equal to 1000 Kb W2 divided by delta TB into W1, and this means dissolving a non-mass of the solute, a non-mass of the solvent, and finding delta TB. Finding delta TB means find the boiling point of pure solvent, find the boiling point of the solution, find the difference between the two, we get delta TB. So delta TB can be experimentally found out, and rest of all, knowing the value of Kb for the given solvent, we can find the molar mass of non-volatile solute. So that is the significance of elevation of boiling point. And the next colligative property is depression of freezing point, which we will see.